Hello students, today we are going to study the finite state machines, that is FSMs. A finite state machine is a generic model for the sequential circuits which are used in sequential circuit design. Like for example, what is a finite state machine? Any machine which has a countable number of states which can be counted. Let's take an example. Suppose I have an LED. Now LED can have two states, either it is on or it is off. So the number of states is 2 here and it is a finite number of states. So this particular machine which I am talking about is a finite state machine. So we can control the output of a finite state machine by controlling the input as well as the previous outputs. So we will see how we design a finite state machine. Let us now see the block diagram for a finite state machine. So we can see it consists of certain inputs. There is an output. There is a clock signal because it will consist of a sequential signal, sequential circuit in between. We have next state logic. So this logic will design how the next state of the circuit is determined. And we have an output logic. This will determine what output is produced. Now we have a feedback. So previous state is also going back through this particular connection, and we get a next state which is stored in the state memory. So we have a memory element also. We can use D flip-flops for storing the bits like zeros and ones. So this complete block diagram shows the structure of a basic finite state machine. These are the various elements present. So the state memory, how we see the memory of the system, it is a set of n flip-flops which holds the state of the machine. So if you have n flip-flops, how many states are possible? 2 raised to the power n. Like for example, I have 3 flip-flops. So 2 raised to the power 3, that is 8 possible states are there for this machine. What is the next state logic block? It is a combinational circuit which will determine the next state as a function of the current state and the input. So input is going from here and the current state is coming from this part through a feedback. Next we have output logic block. It is also a combinational circuit which determines the output as a function of the current state and the input. So the current state and the input is fed to the output logic and we get the output value. So this is the basic block diagram. Now we see the types of FSMs. Like there are two types of finite state machines. One is the Mealy machine and one is the Murray machine. So the distinction is quite clear. In Mealy machine, the output will depend on the current state, that is the present state of the circuit, and the input value. In the Murray machine, the output will just depend on the current state. So this is the difference. Like in Murray machine, the output will not depend on the input. So these are the two types of machines. And state is the output state machine. A Murray type FSM where the current state is the output. So this is a kind of output state machine. In output state machine, what will happen? We will have a Murray type of FSM where your current state is the output itself. So these are the block diagrams which you can go through. Let us now see how we represent the state diagram. So the state diagram represents the states as circles. So in this particular example, we have 4 states. So all these circles are representing the states. So there are 4 states, that is 0, 0, 1, 0, 1, 1 and 0, 1. And the transitions between the states are denoted by arrows and they are annotated with inputs and outputs. How? Like suppose if we consider this arrow. So it is having 0/1. So 0 is denoting the input here and 1 is denoting the output here. So these are the transitions which are denoted by the arrows. Now let us see the analysis of FSMs with the D flip-flops. What we do, we have to determine the next state and the output functions as per the what previous state we are having and the inputs provided. Then we use the functions to create a state or output table which specifies all the possible next states and output for any combination of current state and input. Like for example, let's say the current state is 1, 0 And for example, the input is say 0. So we must be able to define like what will happen to the output and the next state when we give an input of 0 when the current state is 10. So this will provide an exact definition of the FSM. This is a simple example which shows a normal FSM where our X is the input and here our Y is the final output. And in between we are using combinational, these are combinational logics, like this is a combinational logic circuit, this part is a combinational logic circuit. So these are used to define how the next state will change and how the output will change as per the input and the previous state. This is the way the state table is represented. So let's understand this. Here A and B are the present states. A plus and B plus are denoting the next state values. Plus means when the clock signal will come after that, how it is going to change. X is our input and Y is the final output. So this is the way in which the state table is represented. We give the input values, we give the output values, we give the present state and we give the next state. So all these four things must be present in the state table. And regarding the state equations, like how the next state is defined, we can have an equation for that. So next state is denoted by A plus and B plus. So we can write down the expression for A plus and B plus in terms of the previous state. What is the previous state? A and B. And the input X. So we can write A plus as AX plus BX. This is just an example. And B plus we can write as A dash X. This is a simple example how we can write the next state. And Y is denoting the output. So we can see Y is A plus B and X bar. So we can see the output is dependent upon the previous state, which is dependent upon AB, and the input as well, that is X bar. So this is the way, an example to show that how the state equations and state table looks like. Now let us see how we can design a sequential circuit. What are the steps followed? We can see that. So from the description of the functionality of the state or timing diagram, first of all, we design the state table. State table is defined. We encode the states of the state table which contains letters. We can encode them like 10 is A, 01 is B, and so on. Then we find the number of flip-flops required. We choose a type of flip-flop. Then from the state table, we find the excitation tables and the output tables. These will help us in determining the output expression and the next state expression. Then to simplify the expressions, we use K-map technique. We can use any other technique as well, but K-map technique is efficient. And finally, when the expression is obtained, we draw the circuit logic diagram. So these are the steps we can follow in designing an FSM. So now we can see an example of a state diagram. Like this kind of a question can be asked, like design the sequential circuit of the given state diagram. So let us understand what this state diagram actually means. So how many states are there? Can you identify? There are four states. So they are 0, 0, 1, 1, 1, 0 and 0, 1. So there are four possible states in this particular circuit. So how we can start making the table for this? We can identify these like states as A and B. And we can write down all the possible states in a table. So they are 0, 0. Then we have 0, 1. Next is we can take 1, 0. And the last one we can take as 1, 1. So initially we can fill up all the states possible for the system. Now, we are given some transition arrows. Like for example, if I consider this arrow, what does this mean? It means that when the system is in the state 0, 0 and we provide an input 0 to the system, then the system will come back to this state itself. It will remain 0, 0 only. Now let us denote this particular input by a variable x. So suppose I write down x here, and if my system is in the state of 0, 0, this is the present state, and the value of x is 0, then what will be the value of a plus b plus? What is a plus and b plus denoting? A plus means the next state which will be coming, and b plus is denoting the other bit for that next state, because the state is represented by 2 bits in this case. So when we were in the state 0, 0, and when we got an input x as 0, then the state remains the same. It came back to 0, 0 itself. So we can fill a plus b plus as 0, 0. So this is the manner in which we can complete the table. Again, we have to consider one more case for this state, so we can write it down here. So AB is a 0, 0, and the input is 1. So this particular arrow is denoting the same. Input is 1. So it is going to this state. So my x value is 1 in this case. So which state it is going to? It is going to 0, 1. So I write down 0, 1 here. And so on. So this way we can complete the table. So a total of 8 entries we will get, because for each state we have two possibilities, 0 and 1. So 8 rows we can complete, and this way we get the state table or for this particular state diagram. Then what we can do, once we have the table in front of us, we can write down the expression for a plus and b plus. So a plus and b plus are basically denoting the next state. So next state a plus and b plus, we can get the expression in terms of these three, a, b and x. When we get the expression, we can simplify it using any method such as K-map method, and the final expression can be drawn using the logic gates. So this is the manner in which we can design a circuit using the state diagram itself. So understanding the state diagram is very important here. Thank you so much for watching the video.